chapter 1.4, del operator or Nabla. What is the del operator? This is the symbol of Nabla or del operator, the downward triangle. This is different from triangle. Okay, triangle means the increment. So the downward triangle means the del operator. So del is a vector, also can be written in the form of bracket. So you can also write it like this, del over del x, or the partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. Del cannot stand by itself because del is an operator. Okay, operator just like the plus, okay, plus sign or minus sign. So del also an operator. It cannot stand by itself. Okay, next is the definition of scalar function and vector function. Scalar function is the function that has scalar value. So let's say you have a function f, x, y, z equal to x, z squared plus yz. So at point 0, 1, 2, your f 0, 1, 2 will be, okay, just substitute x equal to 0, y equal to 1, and z equal to 2. So your function will be 0 times 2 squared plus 1 times 1 times 2. So this is equal to 2. So you know that this is a scalar. Okay, next is the vector function. Vector function means the function that has vector value. For example, you have vector f. This is vector f, x, y, z. The value is equal to x plus y, I, plus x, y, z, j, plus y, z. Okay, this is vector function. I want to write in the bracket form. It will be x plus y, x, y, z, and y, z. So at point 0, 1, 2, your vector f will be 0 plus 1, 0 times 1 times 2, and 1 times 2. So this is equal to 1, 0, 2. You will get a vector. So that is the difference between the scalar function and a vector function. So before we go any further, let me simplify this subtopic. So now you have the del or Nabla operator with this symbol, and this means the partial derivative del x I plus del y j plus del z k. So del operator can be used to find a gradient, or you can write like this, a gradient f, or you can write like this, a grad f. Okay, this will give you the same meaning. So this f is scalar function. So besides that, you also can find a divergence of vector. You can write like this, div, divergence of vector. This is del dot vector f. Okay, this is divergence of vector. And another one, you can find the curl of vector. So curl f is equal to del operator cross product vector f. So under gradient, you have the application of gradient. So you can find the directional derivative and the unit normal vector. You can use the gradient of f to find the directional derivative and the unit normal vector. So this is what we will learn today. Okay, so now let's start with the gradient. So gradient represents the slope of the function, and you know that slope is the rate of change of the function. So a gradient is a vector and a slope is a scalar. So gradient really become meaningful in multivariable function where gradient is a vector of partial derivative. gradient of scalar function is a vector field that points in a direction of the greatest rate of change of scalar field. So for example, you have this scalar field. So the black area here represent the greatest rate of change. And all these arrows, the blue arrows represent the gradient. So this is the greatest rate of change, and these arrows are the gradient. Okay, look at this example. Consider a room in which the temperature is given by a scalar field T. Okay, let's say you have one room. Okay, this is a room. Okay, so you have F. F here is the temperature T. Okay, assume that the temperature does not change over time. At each point in the room, the gradient of T at that point will show the direction of temperature rises most quickly or decrease most rapidly. So increase or decrease. Okay, let's say you have this point, the red point, and you have the blue arrow. The red area represent the greatest rate of change, and the blue arrow represent the gradient. Okay, so this is the formula for gradient of scalar function. Okay, if f, x, y, z is a scalar function of three variables and f is differentiable, the gradient of f is defined by gradient f. You have to differentiate one by one according to its component. So in this case, this f is the scalar function. Then when you find the gradient, it will become a vector function. Example 1, if phi is equal to x squared y z power of p plus x y squared z squared, determine gradient phi at p equal to 132. So you have to differentiate this phi with respect to x and then with respect to y, and then differentiate this phi with respect to z. Okay, the first one, del phi del x. This is del phi del x. Okay, differentiate this with respect to x, you will get 2x y z power of 3, and differentiate this with respect to x, you will get y squared z squared. So this what you will get when you differentiate it with respect to x, with respect to y, and with respect to z. So after you get the answer, you have to put it together to find the gradient phi. So this is differentiation with respect to x. Okay, this is the answer just now. And then with respect to y, with respect to z. After you combine these three together, substitute the value of point P. 1, 3, 2. So in this case, your x is equal to 1, y is equal to 3, and z is equal to 2. Just substitute these values into your gradient phi just now. So you get this value for component x, component y, and component z. Simplify it, then you will get this answer. 84i plus 32j plus 72k. Now let's try example 2. If phi is equal to x power of 3yz plus xy squared z power of 3. Determine gradient phi at point P, 1, 2, 3. So now let's differentiate it. Okay, with respect to x, with respect to y, and with respect to z, differentiate phi. So del phi del x, you get 3x squared yz plus y squared z cube. And then del phi del y, x power of 3 z plus 2 xy z power of 3. And the last one, del phi del z, you will get x power of 3y plus 3xy squared z squared. Okay, now let's combine it to get a gradient phi. Your gradient phi is equal to del phi del x. Okay, I want to write in the bracket form del phi del y del phi del z. So this is equal to 3x squared y z plus y squared z power of 3 del phi del y x power of 3z plus 2xyz power of 3 and del phi del z x power of 3 y plus 3 xy squared z squared. So at point P 1, 2, 3, your gradient phi will be 3 1 squared 2 times 3 plus 2 squared 3 power of 3 1 power of 3 3 plus 2 1 2 3 power of 3 and 1 power of 3 2 plus 3 times 1 times 2 squared times 3 squared. Simplify this, you will get 18 plus 108, 3 plus 108 and 2 plus 108. This is equal to 126, 111 and 110. In IJK form, which is 126I plus 111J plus 110K. Just differentiate and then substitute the value. Okay, so there are some properties of the gradient. If A and B are two scalars, okay, scalar function, then gradient A plus B is equal to gradient A plus gradient B, and gradient A times B is equal to A times gradient B plus B times gradient A. Application of gradient, which is the directional derivative and the unit normal vector. So the first one is the directional derivative. By using directional derivative, we can generalize the partial derivative to calculate the slope. So the slope is the rate of change of a scalar field in a particular direction. If the directional derivative positive, then there is a increasing in rate of change. If negative, decreasing rate of change. So that is the meaning of the directional derivative. The formula for directional derivative, unit vector A dot the gradient F. So unit vector is A hat here dot with gradient F. Okay, so this is the same value, gradient F or del F. A hat is equal to A divided by magnitude A. So this is a unit vector in the direction of A. And you know that the magnitude of A hat must be equal to 1. Okay, look at example 3. Compute the directional derivative of phi x squared z plus 2xy squared plus yz squared at the point 1 to negative 1 in the direction of a vector A. So this is the formula for directional derivative. So this is A hat. Okay, this is phi, the vector field. Then we have point 1 to negative 1 and vector A. We want to determine whether at this direction the gradient is increasing or decreasing. So A hat dot gradient phi. Okay, first you need to find the gradient phi. Okay, so this is your phi. Okay, just find the gradient, differentiate each of these, so you get this value, and then next substitute the value at point 1 to negative 1. So x equal to 1, y equal to 2, and z equal to negative 1, and you'll get this vector. So your gradient phi is equal to 6i plus 9j minus 3k. And then for A hat, you need to find A over magnitude A. So magnitude A is equal to square root 29, and your A hat will be this value. Okay, this is your A hat. And the last step, A hat dot gradient phi This is your A hat dot this value. Okay, dot product means you have to multiply the first component with the first component plus second component times second component plus with the third component times the third component. Simplify this, you will get 51 over square root 29 equal to 9.47. You can see that this is a positive value. So the rate of change to direction A is increasing. So you can conclude that the rate of change to direction A is increasing. So now let's try example 4. What is the direction along which F decrease most rapidly at the point 3, 2. So when you read the question, what is the direction along with F decrease most rapidly? So decrease means the value is negative. So you want to find the negative value of gradient F at point 3, 2. And then number 2, find the direction U such that U dot gradient F at 0.11 is equal to 5. So the answer for number 1, number 2. Okay, so this is answer for example 4. So unit normal vector is equal to gradient phi over magnitude of gradient phi. The normal vector is a vector which is perpendicular to the surface. Okay, so this is your surface. Then this is the normal vector. Okay, this is the surface. The normal vector must be 90 degree to the surface. And when normals are considered on the closed surface, the normal vector will be always outward pointing. Normal. Okay, this one outward pointing. Normal vector is denoted by gradient phi, and the unit normal vector is gradient phi over magnitude of gradient phi. Example 5. Calculate the unit normal vector at negative 1, 1, 1 for 2yz plus xz plus y equal to 0. So this is the formula. So you have this value. So from this, you have to find the gradient phi. Let phi is equal to 2yz plus xz plus xy. So gradient phi differentiate with respect to x, you will get z plus y. Okay, and then for second component, differentiate phi with respect to y. Okay, 2z plus x. So this is how you get this value. For the third component, differentiate this phi with respect to z, you will get 2y plus x. At point negative 1, 1, 1, your del phi will be 2I plus j plus k. Okay, just substitute x equal to negative 1, y equal to 1, and z equal to 1. Then you get this value. Next, you can find the magnitude of gradient phi. 2 squared equal to 4, 1 squared, 1 squared equal to 1 plus 1. So 4 plus 1 is equal to 6 square root. And finally, you have to combine it. Okay, so the unit normal vector is equal to gradient phi divided by the magnitude of the gradient phi. This is gradient phi and this is the magnitude. Okay, so this is your final answer. Okay, next is the divergence. Divergence operator measures the magnitude of a vector field source or sink at a given point. Okay, let's say you call it as a source when the divergence is greater than 0, which means this is a positive value, and then we call it as a sink when the divergence is less than 0. So this is negative value, and we call it as incompressible when divergent f is equal to 0. So when the divergence f is equal to 0, there are no source or sink. When divergence f is greater than 0, we call it as source. Divergence f is less than 0, we call it as sink. And divergence f is equal to 0, we call it as incompressible. So source means the inflow is less than outflow, and sink means the inflow is greater than outflow, and incompressible means inflow is equal to the outflow. So one of the example of the source is the shower. So this is the inflow and this is the outflow. Okay. Example of the sink. For example, you have water in the sink hole here. And the last one, incompressible, the water in the swimming pool. These are some example. So what is the divergence of vector? If A is a vector, okay, AX I plus AYJ plus AZK. So the divergence of A is defined as the gradient dot A. You have this gradient dot A. So you have to find the gradient of each of these and do the dot product. So your answer will be a scalar. The final answer for the dot product is a scalar. Okay, now look at this example. Given A, okay, if A is equal to x squared yi minus xyz j plus yz squared k. Determine divergence A at point 1 to 3. So gradient dot A. So this is the gradient and this is your A. Del AX del X. So this is your AX. Okay, the first component. Differentiate this with respect to X, you will get 2xy. Okay, so that's why you get this. Del AY del Y. This is your AY. Okay, differentiate with respect to Y, you get negative XZ. And your AZ, this is your AZ. Del AZ del Z, differentiate this with respect to Z, you will get 2YZ. At point 1 to 3, substitute x equal to 1, y equal to 2, and z equal to 3 into your divergence A. So you get 13. This is a scalar. Okay, now let's try example 7. If A is equal to x power of 3, y squared I plus x y squared z j minus y z power of 3k. Determine divergence A at point 3 to 1. Del AX del X 3x squared y squared. Differentiate with respect to X for the first component plus differentiate with respect to Y. Differentiate this A Y. Okay, the second component of your A. Then you will get 2xyz. Then differentiate AZ with respect to Z, you get minus 3yz squared. At point 3 to 1, you will get 3 squared, 2 squared plus 2, 3 to 1 minus 3, 2, 1 squared. So this is equal to 108 plus 12 minus 6. This is equal to 114. A is a vector function, but divergence A is a scalar function. If divergence A is equal to 0, vector A is called a solenoid vector. Okay, so the last subtopic is the curl of a vector. So curl is an operator that describes the rotation of a three-dimensional vector field, it is calculated as gradient cross product with A. Okay. So this is del x, del y, del z. So when curl is greater than 0, it is rotate in the counterclockwise orientation. If curl is less than 0, it is rotate in the clockwise rotation, and if curl is equal to 0, it is irrotational. So how to calculate the curl of a vector? Let's say you have this A, gradient, cross product A. So this is your gradient, and this is your vector A. You just write like this, ijk, there del x, there del y, there del z. And this is ax, ay, and az. The first component, second, and the third component of your given A. Given this A, determine curl A at 1, 3, negative 2. So you just write like this. This is I, j, k. This is the gradient, there del x, there del y, and there del z. And this is your ax, ay, and az. Calculate it using the cross product. Okay, so differentiate this with respect to y, differentiate this with respect to z. Then we will find the first component, I, and then differentiate this with respect to x, differentiate this with respect to z. Then you get the second component, j. And similarly, differentiate this value with respect to x, and differentiate this value with respect to y. You get the third component, k. Simplify this, and then at 0.13, negative 2, just substitute the value of x equal to 1, y equal to 3, and z equal to negative 2 into your curl A. Then you get this vector. So divergence dot product, so you get scalar just now, and the curl is a cross product. Your final answer will be a vector. 2i minus 8j minus 106k. Example 9, this is the answer for example 9. So A is a vector function and curl A is also a vector function. Gradient operator acts on scalar field to give vector field. And then the divergent operator, Nabla dot, acts on vector field to give a scalar field. So you get a scalar. And curl operator acts on the vector field to give another vector field. Okay, magnitude and direction of change.